This is an example problem, an example of using the conservation of momentum to make a prediction. And we're doing a momentum conservation prediction in 2 dimensions. So the problem is I have these 3 particles that are headed in towards each other. And these 3 particles have some collisions, right? They might bounce around each other multiple times, but I'm telling you that they are separate afterwards. So you can see that particle C is heading this way, particle B is heading this way, and particle A is heading that way, for example. But what I'm not telling you is I'm not giving you information at all about the collisions themselves. But I am going to tell you that this system of particles is isolated completely from any environmental issues. So, for example, no air drag, no friction, no gravity. For example. There could be other environmental factors, of course, but in this example, or in stuff that you're getting used to thinking about, I'm saying that this is happening somewhere out in space where there's no air. Stuff is not rubbing on space. There's nothing to rub on out in space. And then out in space, out in the middle of space, there is no strong gravity for these particles to worry about. Okay, so here's how a typical problem gets set up. This could be considered a typical easy problem. Yeah, so typical easy problem. You're given that PA initial, so this is the initial value of the momentum, is equal to, so I'm going to introduce, you could use this as a trick if you'd like. I like to do this myself, but I'm going to say that this initial momentum is 3 momentum units in the x direction. So here is a convenient trick. You just name your own unit, and I'm going to say that the unit is the kilogram times meters per second, the SI unit for momentum. And I'll just call it U. It doesn't, yeah, you could call it a different, you could give it your first name's initial. Yeah, if you wanted to. Okay, so so that is the initial or incoming momentum of A right here. It's one of the givens of a typical easy problem. Here's another given of this typical easy problem. So the momentum of B initial, so I here means initial, I hat means x direction. This one is -2 kilograms meters per second, so a shorthand for our unit of momentum. J hat, so it is in the y direction but downwards. So that's the direction of momentum of B. So actually I kind of drew this wrong. It's better to say that B is headed straight down into the collision zone where they're going to interact with each other. And then I'm also giving you the momentum of the object C initially before the collision happens. This one is 3 I hat plus 4 J hat, and also in kilograms meters per second units. Continuing with the givens, so these are before the collision, and for all we know, there could be multiple collisions, and then after all of the collisions are finished and they are no longer going to bump into each other, or yeah, in this case that's what happens, but after the collisions there are some givens. So PA final, So this is the final value of object A's momentum. So this is kind of funny. I'm in this particular problem, what happens is the momentum is unchanged from before to after. The momentum of object B, this particle here, has become, in the final case, 1 unit of momentum in the I hat direction plus 2 units in the j hat direction. And then here is the unknown. So this is the momentum of object C after all the collisions, or this is our prediction. This is the goal of the problem, or at least the first part of this example problem. Okay, so we have to make a prediction. This is what we want to say. This is how we're going to get a good grade on our test, is we're going to give the vector value of C's momentum if B and A's momentum after the collision are these values, and before the collision, this was everything about the momentum beforehand, before the 1 or 2 or 3 or 10 collisions that happened between A, B, and C. So what we're going to do is we're going to get this using momentum conservation. And the idea is, in particular, we're using momentum conservation for isolated system, which is what I told you from the beginning. So this was one of the conditions in the problem. These were other conditions. These were other specific statements, data that you can use to make a prediction later. So is this. This is an equivalent piece of information, or equivalently important piece of information. So momentum conservation for an isolated system, what this means is that the P total before all the collisions, so that is the total system momentum, here is all 3 parts of the total system momentum, before the collisions, or initial, is exactly the same as the total system momentum after the collisions are done. So the idea is if I was to add up these 3 momentum vectors, that's what I would get. That's the total initial momentum. It is equal to adding up those 3 vectors. And so you can see that I have an unknown here, and momentum conservation for an isolated system for this case, I'm going to have an equation, and I'm going to have a way to get at my unknown vector value. So that's what we'll do in the next page. So P total initial, let's do this one quick. So be really careful, but when you add these things up, what you have to do is you have to add the I hat direction, the x directions together. So here's 3 and 3 more. And then add the j hat. So I've got -2 and 4 more is a net of +2. And then over here, this is the momentum total in afterwards. So this is where the unknowns are. So in the x direction, I've got 3 plus 1 plus something that's unknown in the x direction. So I'm going to write it this way. So P total final is equal to, so 3 plus 1 is 4. And I'll reserve the I hat for a little bit, but plus the unknown C final x direction. Look at all of those subscripts, all in the I hat, right? That's I hat stuff. And then there's a j hat part. So this is 2 units of momentum in the j hat plus an unknown c, object c, final y direction momentum. So I'll put plus p sub c final y direction j hat. And now you can see that if I invoke my physics rule that for isolated system, the momentum before and after is the same value, then you can say that 6u I hat plus 2u j hat is supposed to be equal to 4u plus p sub c final in the x direction I hat plus this stuff, 2 units plus whatever c has in the y direction final j hat, like this. And so you can see that in the I hat direction, 6u needs to be 4u plus p sub c in the x direction, final. And then also 2u needs to match up with all of that stuff. And it's pretty easy to see at this point. So what p sub c final in the x direction needs to be to make up a full 6 is 2. So p sub c final in the x direction has to be 2 units of momentum with a plus sign, actually. So let's explicitly say that. And then in this case, you can see that p sub c final in the y direction has to be 0. And so we can write that p sub c final is a vector equal to just 2 units in the I hat direction. And we have made a prediction. Our prediction is based upon this equation right here, and this equation is only valid for an isolated system. And that is what we have because somehow, right, either somebody tells you that the system is isolated, or you have to make a physics decision and decide that that system is isolated. So let's learn something else about this interesting collision that just happened. We had all of these incoming momentums into some zone of collisions, and then after the collisions are finished, we have outgoing momentums. Yeah, so an interesting question to ask. Let's go learn, or tell me about kinetic energy. And what I mean by this is it would be interesting to ask, I had all of this kinetic energy coming into the collision, and I wonder, how is it related? Is it bigger than, equal to, or less than the total kinetic energy of the stuff afterward? Right? This would be kind of an interesting question. If the total kinetic energy afterward is bigger than the total kinetic energy going in, we could say that maybe there were some extra energy around, or like small explosions or super elastic collisions things going on. If the total kinetic energy afterwards is equal to the total kinetic energy before, that feels more like elastic. And then if the total kinetic energy before is bigger than the total kinetic energy afterwards, then somehow kinetic energy got lost a little bit. It must have gone somewhere else. Yeah, maybe got stored in a potential way, or got what's called thermalized into energy associated with a temperature rise, like an increasing temperature, or even honestly, a chemical change. Lots of different ways for kinetic energy to seem to disappear and become a different form of energy.